Okay, in example 6, we have to see if these 3 points are part of this relationship. So what we're going to do is we're going to take xy and plug it in and see if it's true. And then we're going to take this xy and plug it into here and see if it's true. And then we're going to take this xy, plug it into here and see if it's true. So what we have here is 2 squared times -5, that's a -20. -5 squared is 25, and that equals 5. So this one is defined implicitly in this equation. If I try 1 and 3, I get 1 squared times 3, which is 3, plus 3 squared, which is 9, and 12 does not equal 5. So this one is not defined by this equation, this relation. Then I plug in 2 squared times 1, and this one works. So this one is defined by this relation. Now I'm asked if it's a function or not. Well, I have 2 going to 2 different y values, so no, it is not a function. The next thing that we're going to do is that sometimes we need to solve for y. A relation may not be a function, but if you solve for y, you find that the relation defines multiple functions implicitly. Implicitly means it's not y equals. So here we have this one. It's got x's and y's, and we figure, what are we going to do? Well, let's factor it. And once we factor it, we can take the square roots, and we find that x plus y equals plus or minus 1. Solve for y, and we have 2 different equations. This is your implicit equation, and it really is 2 parallel lines, not a function. It doesn't pass the vertical line test. Now another thing we can do is define a function parametrically. What we do here is we have x equals t plus 1 and y equals t squared plus 2t. Notice t is another parameter. All it is just another parameter. We could be studying motion where we're looking at vertical motion as it relates to time versus horizontal motion as it relates to time. So I plug in -3 all the way to +3 into each one of these, and I find my x value. So I plug in -3 plus 1 and I get -2. And then I plug in 3 squared plus 2, -3 squared plus 2 times -3, and I get 3. So I plug in t for every one of those. These are now my points. Part B says find an algebraic relationship. That means I'm going to solve for t, or I'm going to get rid of t. So I take this easy one and rearrange it so I solve for t, plug it back into here, expand, and simplify, and now I've got an algebraic expression. The t's are gone. Now this is a parabola. We have seen it before. It's a parabola that's shifted down. However, when we graph it, we can only graph the points that are given us. So I put it on a grid, and I graph these points here, which makes up this part of the parabola. Example 9, we're using a graphing calculator in parametric mode. So here's your equation, and what I'm going to do is take my graphing calculator, and I'm going to put it in, turn it on, and I'm going to put it in parametric mode. Notice we usually have done things in function mode. If you go over here, it's parametric mode, and then when you press the y equals, you'll get this x1 and y1. You need to enter this. Now you ask where your t is. Remember when you would press the x for function? Well, you press the t, and the t shows up, and you get t squared plus 2t and t plus 1. Now I have to figure out how this works, so hold on. Using this graphing calculator, we're going to put the points between -3 and 3. So I go to my window, and I want my t values to be between -3 and 3, and I want it to go into increments of 1. I don't have decimals up here, so I'm only going to go in increments of 1. I happen to put it between -10 and 20, but we can play with the window once we see what it looks like. Now what I'm going to do is I'm going to hit graph. Notice the equation's in there, my window is set, and now I hit graph. This is what my graph looks like. Now if I look at this, is it a function? No, because it fails the vertical line test right here. So it is not a function. Now it asks me to find the algebraic relationship. All that means is get rid of your t. So I solved for t, and then I plugged it back into the x equation, expanded the x equation, and there's what I get, x equals y squared minus 2. That is not a function. Now inverse relations and inverse functions. a relation has an inverse, when the point on the relation is AB, the inverse would have the point BA. And if a function passes the horizontal line test, then its inverse is a function. That means I don't have to draw the inverse. All I have to do is look at the original function. If both the function, the original relation is a function, and its inverse is a function, then we say they're one-to-one. To find the inverse algebraically, we switch the x and y. We solve for y. Two characteristics. The functions and their inverse reflect across the y equals x line, and if the original has this point, the inverse has this point. This is the notation we would use. This is the inverse function. It is not a reciprocal. You could also write f of g of x. And this is also the inverse. And when you compose these two functions, you will get x. So what does it mean to apply the horizontal line test? These are my four graphs. I want to know which ones are functions. So looking at the graph itself, this one passes the vertical line test, so it is a function. This one does not pass the vertical line test, so it is not a function. Neither does this one pass the vertical line test. Graph 4 does pass the vertical line test, so 1 and 4, these two here, are functions. Now I want to know if the inverses are functions. I don't need to draw the inverse function. I just do a horizontal line test on this graph, and yes, its inverse is a function. I do the horizontal line test here, and yes, its inverse is a function. I do the horizontal line test here, it is not. I do the horizontal line test here, it is not. So the only two functions that the inverse is a function is 1 and 2. Now if the original one is a function and its inverse is a function, this graph here is the only one that's a one-to-one function. Now how do we find this algebraically? This says f of x, and sometimes using these symbols can be confusing. So I'm just going to rewrite the original with y, and then I switch the x and the y's, and then I cross multiply 1 times y and x times y plus 1. And now I'm going to distribute, put the y's together, factor, and solve for y. So now what I have here is this is the inverse function. It is not a reciprocal, it is an inverse. Let's look at example 12. Here is my original function, and all you have is this graph. If I want to find the inverse, I draw the dotted line, which is the y equals x, and I literally will take this and reflect across it, and this is now my inverse function. Alright, now they want us to show algebraically that these are inverse functions. That means when I compose them, when I do f of g of x, or I do g of f of x, they better equal x. So I start off with my function, I input my g function. My f function is just whatever it is cubed plus 1, since that's my input, I put it in there. A cube root that's cubed is exactly what's inside, and I simplify, and I get x here. G of f of x. I take the g function and I plug in the f function. Now the g function says it's the cube root of whatever my input is. Here's what my input is. So I put x cubed plus 1 minus 1. These go away, and the cube root of x cubed is x. Notice these two both equal x. That means the original is a function and its inverse is a function. Now the very last one that we're going to do for section 1.4 is finding an inverse function. Here is my original function. It does have an inverse function, and we need to find out what it is and state any restrictions on the domains. What's nice about inverse functions and the originals is that the domain of the original is the range of the inverse, and the range of the original is the domain of the inverse. So here I have x plus 3 has to be bigger than or equal to 0, and I solve, so there is the interval notation. That means that that's what the range is going to be for my new function. Now I take my function, y equals the square root of x plus 3, I switch the x and the y. To get rid of the square root, I have to square both sides. Now I have x squared equals y plus 3, and I solve for y. Now looking here at this original, okay, y has to be bigger than or equal to negative 3, which matches that. And if this is my range, it will have to be the domain for this one.